जब हम अब डिस्कस करेंगे एक्चुअल वेपर साइकिल जो होता है और उसकी डेविएशन क्या होती है आइडियलाइज वेपर साइकिल से। तो जिसमें हमें पता है कि जो हमारे पास एक्चुअल साइकिल होगा उसमें हमारे पास इरिवर्सिबिलिटीज होगी, जिस तरह पंप में इरिवर्सिबिलिटीज होगी, जैसे ड्रॉप होगा टरबाइन में तो फ्लूइड फ्रिक्शन की वजह से, तो जिस वजह से हमारे पास जो एक्चुअल साइकिल है वो डेविएट करेगा आइडियल साइकिल से। जिस तरह हमको पता है आइडियल साइकिल हमारे पास बिल्कुल ये स्ट्रेट जा रहा होता है ऊपर, ठीक है, आइसेंट्रोपिक होता है, फिर उसके बाद हमारे पास ये मैक्सिमम प्रेशर होता है, फिर उसके बाद ये यहाँ से एक्सपेंड होता है और हमारे पास दोबारा ये कंडेंसर में चला जाता है। तो जिस तरह हम देखें यहाँ पर तो ये जो हमारे पास डार्क लाइन है प्रोमिनेंट, ये हमारे पास आइडियल साइकिल है और जिसका डॉटेड जो है ये दिस इज एक्चुअली एक्चुअल साइकिल। सो as you can see there is irreversibility in pump from 1 to 2, so this is the deviation, and then other deviation is the boiler pressure drop in the boiler. So as you can see the actual is down here and the ideal is quite up from here, and same goes for the turbine. So actually we are looking, when we will compare actual and idealized, we will be looking at these two. We will be looking basically at irreversibility in the pump and irreversibility in the turbine. So this is how we call it 1 to 2. This is isentropic, or this is 1 to 2. Basically, this is actual. So isentropic was ideal, and A represents the actual. Similarly, this is actual and this is ideal. This line is very straight. Ideal, it represents the isentropic process. So these are the efficiencies formula for the efficiencies for the pump and efficiency for the turbine. We will basically be subtracting the actual efficiency from the ideal, and these ratios will come out from that. So here H2S was this isentropic one. So if you want to calculate the efficiency of the pump, so what we are gonna do is, here is our H2S is isentropic enthalpy. So we're gonna minus it from the actual, which is 0.1 H1, and then we're gonna divide it by the efficiency of 2 at the actual point minus the initial. So basically these efficiencies will be given in the numerical. So let's look at the problem. Steam power plant operates on the cycle shown in figure if the isentropic efficiency of the turbine. So isentropic efficiency of turbine and pump are given. Thermal efficiency of cycle we have to determine, and the net power output of the mass flow rate, and this mass flow rate is given. We have to find net power output. So this is basically the efficiency diagram. These points are given to us. So for the pump of work input, what we're gonna do, we know the formula of work pump in terms of the specific volume and pressure. So we will only divide by the efficiency of the pump. So work of pump will be determined by like this. For boiler input, we have, this is boiler input H4 and H3. So H4 minus H3 will be boiler input. This is H4, H3. So we will find out H3 by the given points at here. This is our pressure. Pressure and temperature are state 3 are given, so we will find enthalpy at point state 3. For turbine work output, we will in the pump we divide the efficiency which is given, and in the turbine we multiply it with the efficiency. So this is turbine workout H5 minus H6, and this is efficiency of turbine. Total net turbine work minus pump work, and for the efficiency work net divided by 20. So net power output is required, mass flow rate is given, we will multiply it with the work net, we will get dot net power output in megawatt. So another example, consider a steam power plant that operates on simple ideal Rankine cycle. Net power output 45 megawatts. Steam enters the turbine at this is steam into the points are given and cooling the condenser pressure is given. Mass flow rate is water is given. PS diagram, thermal efficiency, mass flow rate of steam, temperature difference of rising water. So here it is. The states are given in this simple ideal Rankine cycle. So no reheating is taking place. No efficiencies are given of the pump and the turbine. So for the state one, it is saturated liquid state. So H1 pressure and temperatures are given, and Pascal condenser pressure. So for the work of pump, specific volume V1 is known, P2 minus P1. P2 is 7 megapascals and P1 is 10 kilopascals. 7 megapascal is here. It says steam enters the turbine. So this is a turbine inlet and steam enters the turbine at 7 megapascal. So quite messy. So that's how you find the work of turbine. For we know this formula, work of pump in terms of the enthalpy difference is H2 minus H1. We will find H1 work of pump. We will find H2. For P3 we know pressure at 3 and temperature at 3, which is the highest temperature. We will find H3 and HS, H3 and S3 entropy. We know the P4. We know P4, and this is P4 condenser pressure, and this is isentropic process. So S3 is equal to S4. So if you want to find the enthalpy of H4, first we will determine the quality, the state at which this point lies. For that, we know S3 and S4, and we know P4. So utilizing that, we will find the quality export, and export comes out to be 0.82, which means it is a saturated liquid. It lies inside the dome, and it is a mixture, saturated liquid vapor mixture. So we will utilize this formula by using S4 and X4. We'll find Hg and HFg, and X4 we already know. We'll find H4. Now we find enthalpies and all the state. Either in Rankine cycle problems, we try to find enthalpy at all the states, because the parameters like work input, work output are all determined by the enthalpy differences. Likewise, in other problems like the refrigeration problems, we try to find the temperatures at all these states, because they are defined by the formula we are using in the refrigeration cycles are of temperature differences. So that's what Qin is equal to H3 minus H2. Qin is H3 minus H2. H3 minus H2. Q out is basically H4 minus H1. Work net Q in minus Q out. This is efficiency. This is for the mass flow rate of the steam. So we know the work net is equal to mass flow rate divided by work net. So we found out the work net. Okay, we know dot work net, which was given. Power output 45 megawatts, which is work net, and we will find the mass flow rate of the steam. For the heat rejection of the cooling water, we know Q is equal to MC delta T. If we want to find the change in temperature, we know the Q dot out. For Q dot out, it will be same like this, dot to the opposite side and small q. This is Q out, we already know. H4 minus H1, M dot, we know already know from here, steam. So we will find Q dot out. So if you want to use this formula, Q is equal to MC delta T. If you want to find a temperature increase, so Q dot out we have found from this formula. Mass flow rate of water we know 2000 kg per second, and C is a constant. So specific heat constant for 0.1 kilojoule per kg degree centigrade or Kelvin. So this was it. So this is a simple theoretical concept how we can increase the efficiency of a Rankine cycle. So basically, main purpose of the Rankine cycle is to increase the average temperature at which. So basically, if the temperature of the steam is increased, so that is directly proportional to the efficiency of the turbine or steam power plant's efficiency. So if we can kind of increase the efficiency of the average temperature at which the steam is supplied to the turbine, so it will increase the efficiency. Or uh, and and subsequently, what we can do is to decrease the rejection temperature, average rejection temperature or the condenser temperature. So that's also going to result in the increased efficiency of the steam power plant of the Rankine cycle. So this is mentioned over here. If we can lower the condenser pressure, if we can lower, so this was the actual condenser pressure. If we can kind of lower the condenser pressure, the turbine will have more time to expand and thus it will give more work output. But what it's going to do is this will be the added work net that we will be getting. But it's also going to increase the pump work. The pump will have to do more work to pump the liquid up to the original point. And one other thing is here it is a saturated vapor, and here it's gonna be in mixture. So it's gonna increase the mixture content of the uh, content in the condenser. Mixture content of the steam will be increased if we decrease the condenser pressure. So another is increase the T average pressure, temperature. So basically it's saying that this was our actual point. So if we can reheat it and make it superheated, so this will be the added work net that we'll be getting, and also it's going to decrease the moisture content, which is good for the turbine blade's health. So and the work of pump is the same. So superheating is quite efficient. Another way is to increase the boiler pressure. So this was the boiler pressure. If we can increase the boiler operating pressures, so it's gonna give the same superheated steam to us, and but this will be the decrease in work net, but this will be the increase of work net, and the mixture content of the steam will also increase. Work of pump will also be increased. So these are the pros and cons. So simple question, theoretical. Consider a simple ideal Rankine cycle. This is an ideal Rankine cycle. 1 to 2, 2 to 3, and 3 to 4, and 4 to 1 heat rejection. So what is the effect of lowering the condenser pressure? If the condenser pressure is low, so heat rejected will be decreased and everything else will increase. Work of pump will increase, heat supplied will increase, and heat rejected will only decrease. Cycle efficiency will also increase, moisture content will also increase. Effect of increasing the boiler pressure, heat rejected will be decreased, everything else will increase. Work of pump increase, heat supplied increase, turbine efficiency increase, and cycle efficiency increase, and moisture content also increases. Effect of superheating the steam, same. The pump work will be same, quality will be improved, increase, moisture content in other words decreases, and everything else will increase. Efficiency, Q supplied, work net. So this was the end of it. Steam power plant. Consider a steam power plant operating simple Rankine cycle. Simple Rankine cycle. Steam enters the turbine. 3 mega. So this pressure is given. 3 megapascal, 350 degrees centigrade is condensed in the and condenser pressure is given. Determine thermal efficiency. So we'll find all the enthalpies at all the states. For P1, P1 is 75 kilopascals, and this will be so P1 we know saturated liquid HF, VF, and for P2 we know this is This is the 3 megapascal turbine inlet pressure and temperature. We will find S2 will also be equal to S1 isentropic process compression. So work of pump will be specific volume P2 minus P1. We know the specific volume. We know the P2, P1. Work of pump in terms of the enthalpy difference is this. We will find enthalpy at point state 2. For state 3, we have pressure and temperature. We find entropy enthalpy. For enthalpy at point state 4, we know the P4. We know S4 is equals to S3. We will try to find the quality or the state at which this point 4 lies. We don't know whether it is saturated liquid, saturated vapor, or the mixture. So for that, we at P4 and S4, we found S4 and SG, and our S4 was coming in between. So therefore, we concluded that it is a liquid vapor mixture. So we found out X4, and with the help of X4 and S4, we find HF and HG, and we find H4. Now all the enthalpies are known. Q in H3 minus H2. Q in will be H3 minus H2. Q out will be H4 minus H1. Work net will be efficiency will be 1 minus Q out over Q in, or work net over Q in. Work net will be Q in minus Q out. So that's how you can do it at another way. Work of turbine will be H3 minus H4. Turbine work minus work pump will give you net work, and net efficiency will be found like this. Consider steam power plant operating on the ideal inclined cycle steam turbine at 3 megapascal. 3 degrees centigrade is condensed in 10 kilopascal. So steam turbine inlet temperature, pressure, and condenser pressure are given. Thermal efficiency. Thermal efficiency where steam is superheated and the temperature remains the same. Thermal efficiency if the boiler pressure is raised from 3 megapascals to 15 megapascal, and in the turbine inlet temperature is 600 degrees. So for the case one is simple, like the previous one, 10 kilopascal, 3 megapascal, P3 is not. We will find enthalpies at all state. For P1 saturated liquid, H1, E1, P2, S2 is equals to S1. We will find H2 with the help of work pump. Then in enthalpy difference, we will find H2. For P3, we know P3, P3, we will find H3 and S3. For P4, we again try to locate the saturated mixture of vapor. We will find X4. So S4 is equals to S3. We found out X4. At these points, we located SF and SFG, and with the help of that we found X4 coming out to be 0.812. So with the help of this and this, we found HF and HFG, and then we found H4. Now we can find all the qualities through H3 minus H2, H4 minus H4. This is efficiency. So this is thermal efficiency increased 26 to 33.4% as a result of lowering the condenser pressure from 75 in the previous problem to 10 kilopascal in this problem. We lower the condenser pressure and efficiency increased. But what also happened is the moisture content also increased. In case B, it says that state 1 and 2 remains the same. Enthalpies, we have superheated it to 600 degrees centigrade. So we try to find these new enthalpies, H3 and H4. And X4, look, moisture content also is decreased. As we know, in superheating, the moisture content decreases. So we again find Q in, Q out, efficiency increased. Efficiency has increased and the moisture content decreased. For part C, you said you have to increase the boiler pressure. So we try to find the state 1 remains the same, but state 2 is changed because of the boiler pressure. So we located H2, H3, H4, X4. The quality moisture content has increased. We find Q in, Q out, and the efficiencies. So this is giving very much higher efficiency because of the increased boiler pressure. And efficiency moisture content has increased. because of the boiler pressure. So that's how basically you have to find the enthalpies at all these states by using the pressure and temperatures and these relationships. S4, S3, where the processes are isentropic, S3, S4 isentropic, S2, S1 isentropic. So you find. So this is another problem with saying net work output and the thermal efficiency of the component and simple ideal Rankine cycle are to be calculated and compared. Steam venters are defined in both cases as 10 megapascal. So the higher up pressure is given and the condenser pressure is also given. Rankine cycle, the condenser exit state is saturated liquid. So ideal Rankine cycle, condenser outlet, condenser exit is saturated liquid, means condenser exit liquid, state 1 is saturated liquid, and the boiler inlet is saturated liquid. Boiler inlet, this is basically boiler inlet saturated liquid, and the boiler inlet is saturated liquid. Okay, so Rankine. Okay, this is Rankine condenser exit. Okay, and the corner cycle, the boiler inlet. So this is corner boiler inlet. Boiler inlet is saturated liquid. So this is boiler inlet in saturated liquid in corner cycle. So basically we have to find network output and thermal efficiencies. So we will try to look at enthalpies at all these states. H1, HF at 20 kilopascal, V1, VF. Try to find work of pump. P2 minus P1. Then from the work of pump we will find enthalpy differences and we will find H2, P3, and H3 as it said is saturated. it will be saturated vapor. Quality will be 1. In ideal Rankine cycle, we find H3 and S3. From the have P4 and S4 is equal to S3. We will try to find the quality of this state. So quality is saturated vapor. We will use this relationship at X4 and S4. We will find HF and HFG and find H4. Q in H3 minus H2, Q4 H4 minus H1. Work on net Q in minus plot, and this will be efficiency 35.3. For Carnot cycle analysis, this is a simple Carnot cycle, ideal Carnot cycle. For P3, it is saturated liquid, X3 will be 1, we'll find H3 P3. T2 will be equal to T3 as constant temperature processes, isothermal process. So X2 will be 0 as it is saturated liquid. Quality of saturated liquid is 0. By utilizing these two, we'll find H2 and H2. For P1, this is the mixture saturated mixture region. So we know the condenser pressure, we know S1 equal S2, and S2 we have already defined. We'll find the quality, and then from this quality and this entropy, we'll find HF and HFG and find H1. Then we will use this relation for Q in. Where does the Q in is taking place? In the boiler, H3 minus H2. Q out will be H4 minus H1. Work net will be Q in minus Q out, or 1 minus Q out, or work net over Q in will be efficiency. Corner efficiency is 43, which is much higher than this ideal Rankine cycle, suggesting, and it's quite reasonable and quite logical that efficiency of Carnot cycle will always be greater than any other cycle, ideal cycle. So this is another ideal Rankine cycle, but we saw in the previous example that increasing the boiler pressure is the most efficient process, and the efficiency which came out in increasing the boiler pressures case was much higher. I think it was 43. much higher than the other two cases, the superheating and the condenser pressure lowering. So what are the methods to utilize this process to get the most out of the Rankine cycle's efficiency? So how we can take the advantage of increased efficiency at a higher boiler pressure? Now, the only problem with that is the moisture content we are receiving at the turbine outlet, which is a metallurgical limit, and it's going to affect the life of the turbine blades. So one way is to superheat the steam to very high temperatures before you enter the turbine, so it will eliminate the any moistures. And another way is to expand the steam in turbines in two stages. So basically, and reheat in between. Otherwise, modify the simple ideal mechanical cycle with the reheat process, which is very a non-phenomenon modern days, commonly used in steam power plants. So this is basically a reheat cycle. So what we do is to from condenser we pump the fluid into the boiler, and then in the boiler as it goes to the high, so we use a stage high pressure and low pressure, and what it does from the high pressure turbine, it will its temperature will be lowered as it passes through the high pressure turbine. From that, we will again recirculate it into the boiler. It will be reheated, and again it will be bring back to the low pressure turbine, and then it will again give us the work output. Temperature will be lowered, it will go to the condenser and then again into the pump. So that's how our reheat Rankine cycle kind of work. And as you can see, we try to bring back, we try to reheat the steam back to the temperature at the inlet of the turbine. So temperature at outlet T5, we try to bring it back to the T3, which was the inlet of the high pressure turbine. Basically, in boilers we have constant pressure heat addition. P4 will be P5. So P4 will be P5, constant pressure reheating. So this is the first expansion, okay, and this will be the second expansion by the turbine. And meanwhile, this will be the reheating process taking place in the turbine. All the other processes are same. So if you want to find the Q in this time, so Q in will be, how will you find Q in? There are two processes in Q1. First Q1 will be from a high pressure 3 to H3 minus H2. Another will be this expansion H5 minus H6. Sorry, H3 minus H2, and another another Q in, we will reheat it. This will be H5 minus H4. We will talking about Q in. So if you want to find the work of turbine, so there are two turbines this time. We will add them basically. So how we can add them? Basically, this is one turbine, 3 to 4, one expansion, H3 minus H4. This is second expansion, H5 minus H6, and we're gonna add them together like this. We will find the turbine out. So here it is asking how do the following quantities change when a simple ideal Rankine cycle is modified with reheating. As your mass flow rate is maintained the same. So pump work is same. Pump work remains the same. The moisture content decreases. So it is best. And this was our purpose, to decrease the moisture content at this state, and everything else will be increased. Our efficiency will increase, turbine expansion will increase, Q in will be increased, average temperature will increase. So that's why it. Now we'll try to solve a problem. Consider a steam power plant operating on the ideal reheat cycle. So it says reheat cycle. Steam enters a high pressure turbine at 15 megapascals, 600 degrees centigrade. So high pressure steam at state 3 and condense in the condenser pressure. Condenser pressure is given 10 kilopascal. If the moisture content of the steam at the exit of the low pressure turbine, moisture content of the steam and the exit of the low pressure turbine. Exit of low pressure turbine is this. So X4 is basically given. Pressure at the steam should be reheated. Pressure T5 is asked, to which it will be reheated. Thermal efficiency of the cycle assumes steam is reheated to the inlet temperature of the turbine. High pressure turbine. High pressure turbine inlet was T3. Steam reheated is T5. So he is saying T3 and T5 are equal, which was our assumption in the earlier topic. This is basically a reheat cycle. These states are known. So we will try to find the enthalpies at all the states. State 1, pressure 1 is given. It will be a saturated liquid. HN1 will be HF, V1 will be VF. For P2, we have this pressure, low pressure, high pressure, steam pressure, and S2 equals to S1. We can find S1 from this, and from work of pump in terms of the specific volume and pressure difference, from enthalpy difference, work pumps formula expression, we can find H2. And state 3, P3 and T3 are given. P3 and T3 are given. We can find H3, S3. P6 for the state 6, pressure is given. And H6 is also given. H6 was also given. H6 is 0.896. Okay. So 0.896 is the H6. So now what we can do is, it is a saturated mixture. We will apply this expression. We'll find SFG, and we can find SG by using PG and SG. PG and SG, we can find HF and HG. HF and HFG, and HG we already know, we can find HG. On state 5, we know T5. We know T5 was equal to T3, and S5 equals to SG. S5 isotopic process. SG, S6 is already known. We can find P5, H5. For P4, we already know. P4, we already know, equal to so P4 will be equal to P5, constant pressure reheating. P4 will be equal to P5. S4 equal to S3. Again, isentropic. So S4 equal to S3. We can find H4, T4. Q in will be like this. First Q in will be H3 and H2. Second will be H5 minus H4. H5 minus H4, and Q out will be heat rejected will be from S6 minus H5. So not the expansion. Okay, you can find efficiency like this. Okay, a steam power plant operates on the ideal reheat Rankine cycle. Ideal reheat Rankine cycle. These are the pressure and temperature given. Leaves steam enters the high pressure turbine at 8 megapascal and 500 degrees centigrade. So this pressure and temperature are given. Leaves at 3 megapascal. P4 is given. P4 is given. Steam is then preheated at constant pressure to 1500 degrees centigrade. So P4 and P4 and P5 are given 1500 degrees centigrade before it expands to 20 kilopascal in low pressure turbine. Expands to low pressure turbine. So this is 20 kilopascal expansion in the condenser. Pressure is given. So what we have to find, determine the work output and thermal efficiency of the cycle. you will find all the enthalpies H1, V1, work from H2, P3, T3, P4, S4 equals to H3. You find H4, P5, P5 will be P4, 3 megapascal. P5 is already given constant pressure, temperature, heat addition, and temperature will be same. Same is then reheated at constant pressure to 500 degrees centigrade. This is P5 is given. This is not constant temperature, constant pressure. P5 is given, we can find H4, H5, 6, H5. P6 condensation pressure is given. S6 will be S5 isotopic process. You can find the quality that using which quality and entropy you can find HF and HF dead state, and utilizing H6, FG and HF we can find enthalpy at state 6. Now we know the enthalpies at all the state for the work of turbine. So it's said the turbine work out. For the turbine output, we have to find the expansion processes. So what we are going to do, so basically there are two expansion processes, two turbine. So one is from 3 to 4, and there is 5 to. We're going to add them together, their enthalpy differences, and then we're going to add them together. One will be H3, higher efficiency, enthalpy minus lower enthalpy, H3 minus H4 plus H5 minus H6. So that will give us the work of turbine. For Q in will be same. Because it is reheating, there will be two Qs, one from H3 to H2 in the boiler, and then they again in the boiler, H5 minus H4. For work net, work of turbine minus work of pump, efficiency will be work of net over Q in, 38.9. So the last topic is about the boiler. And simple. Boiler is a pressure vessel which is used to supply the steam for the power generation purposes, for other purposes like heating. So they're basically what comes like boiler shell, combustion chamber where the combustion takes place, a grate where fuel is burned, furnace to supply the heat basically, heating surface, mountings, accessories like pressure gauges, like the pressure gauges, safety valves. This is a furnace, grate where fuel is burned, burner basically like a stove, ash pit where ash is collected. So safety valve, spring loaded safety valve, and basically is used to prevent excessive pressure from building up at the boiler. As you know, the boiler explodes, and it's very hazardous to, in order to avoid the boiler explosion from the excessive pressure buildup in the boiler. We use these safety valves as mountings on the boiler. So what it does is it is meant to endure a specific value of pressure, and when it exceeds, the safety valve basically opens and the excess pressure is released into the atmosphere, and thus avoiding any boiler explosion due to the pressure buildup, excessive pressure. These are pressure gauges for the indication for the visual inspection. Fusible plug, same. Likewise, excessive pressure is dangerous for the boiler health. Same wise, excessive temperature is also hazardous to the boiler life, and it causes various thermal stresses on the outer surfaces of the boiler. So we use a fusible plug, and whenever a certain limit of the temperature is reached, the fusible plug basically fuses, and the entire boiler operation shuts down. This avoids any damage to the boiler. So there are basically two types of boiler: fire tube boiler, water tube boiler. Fire tube boiler, as the name suggests, fire in tube. So basically there will be hot steam in the tube, and the water will be outside in the shell region. So these are basically used for low pressure purposes, lower initial cost, pure control, simple operation. And as drum is exposed to water, so there's an increased risk of explosion, It's not safe as compared to the other boiler. Large water volume, and there is a poor circulation, and there are water tube boilers, as the name suggests, water tube. So water will be in the tubes, and the hot steam uh, coming out from the combustion gases will be in the shell region of the boiler. Usually these are high pressure boilers, high capacity, and skilled worker is required. Initial cost in the fire tube boiler is less, and whereas in the water tube boiler they are high capacity boilers. So their initial cost is setup cost is very high, and skilled operator is required. Boiler operator is required. More control than fire tube boilers, but it is quite safer, as you can see there are more controls on it, thus giving it making it a secure environmental device. There are a lot of pressure gauges, computerized safety valves mechanisms. So but it is expensive and complicated to operate. So that was a end. So now we're gonna stop right here.